Alright, we're going to start with 3, 6, and 10, and for all three of these we're going to use the same experiment. So let's just define each part of this as we talk about these different words. The experiment we're using is pick a number from 1 to 50. Okay, pick a number from 1 to 50. They use the word integer. This just means numbers as we typically think of numbers that we would actually pick. We're not going to pick decimals or anything. Anyway. So this is our experiment. So number 3 describes an event. What's the event? The event in 3 is that you pick an even number. Pick an even number. Okay. So what's the probability of an even number? In case you haven't caught on to this, when we were going to write probability of something happening, just put probability, parentheses, description of the event, and then close parentheses. That's it. So the probability in the event here is that you get an even number. Okay, so what's the probability of getting an even number from 1 to 50? Well, 1 to 50 is set up nicely. It's from the beginning all the way up to this nice round number here, and if we take just a few seconds and think, half of them are even, or 25 of the 50 are even. There are 50 total, so the number of outcomes in this event, getting an even number, is 25. There's 25 even numbers. The total number of events is 50. There are 50 ways to pick a number from 1 to 50. So that's it. 25 and 50, or 1/2. Okay, number 6. A prime number is chosen. So the event in 6 is prime number. Get a prime number. I don't know all the prime numbers off the top of my head. We're going to have to just investigate here. And for our purposes, 1 is not prime. 2 is prime. Okay, prime number being one that's only divisible by 1 and itself. Okay, so somehow by that definition, 1 is not prime, 2 is. 2 makes sense. 2 is a weird one. It's the only even prime. You know, all even numbers at least have 2 as a divisor, but 2 is not among them because only 2 and 1. Anyway, let's just list them all out. 2, we got 3, 5, 7, 9, no, 11, yes, 13, no, 15, 17, 19, 21, 23, 25, 26, 27, 29, 29, 31, 33, 35, 36, 37, 37. Let's see. I'm going to bet on 37 being prime then. 39, 41, pretty sure about that one. 43, I think so. 47, I think 47 as well. Okay. Alright, we're just going to go with that. 47 and 48, 49, 49 of course is 7 squared, so I think we're good here. If we want to test it out, we could just pull up our calculator, and we can just, let's see, we do 11, 17, 23, 29, 31, 37, 41, 43. So here's what you should think about when you go through and think, is this prime? 2, definitely not. 4, obviously no. 3 is not because you add these digits together. They're not divisible by 3. 5 is no. It doesn't. Notice no 5 or a 0 at the end. 6, no, because it's not divisible by 2. So no even number is going to go into this. So we think 7, and I know 7 is going to go into 49, so it's not going to go into 43. 8, no. 9, no. 9 would, since 3 didn't go into it, 9 is not going to go into it. And we really have gone far enough. One thing that you may not know is if you're thinking about testing a number to see if it's divisible by something, you only need to go as far as its square root. even though that square root will be maybe a weird number. So like, let's look at the square root of 43. 6.55. So once we got to 7, we had already gone past the square root, and so we don't need to think about it anymore. Because if the ones that were before the square root were not divisors of the number, then nothing after the square root will be a divisor either. Okay, and we'll leave a proof for that for some other time, or maybe never. So 43 is prime. 47, let's think about 47. No even numbers, so let's think 3. No, you add those together. That's not let's see, 7. No, it's not, the sum of these two digits is not divisible by 3, so not 4, not 5, not 6, not 7, or 8, or 9, and we're past it, right? The square root of 47 is going to be less than 7, so we've already done our due diligence, and we don't have to worry about it anymore. So we do have all the prime numbers here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 11, 12. 15 out of 50, or 3 out of 10. Okay, let's see. Yes, we agree with the book. So here's something, okay, just as far as a vocab thing. The experiment is picking a number from 1 to 50. The event for number 6 is picking a prime number, and to count all of the outcomes in this event, the event is picking a prime number. These are all of them. These are all outcomes. Getting a 2 is an outcome. 3, 5, any number, since picking a number is the experiment, any number is an outcome. So we just listed all the outcomes in this event. Okay, so we could just like say outcomes. Alright, just all that vocab is good to know. Number 10, the event described is perfect cube. And this is a funny thing. It's almost counterintuitive, but then it makes a lot of sense. If you want to think about the perfect cubes, you think, okay, so what's a perfect cube? Like I know 27's a perfect cube. I know 8's a perfect cube. But how do you know you got them all? Well, you say, let's start with the smallest one actually be 1 cubed. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. And 4 cubed is 64, so that's past 50. So there's just 3. 1, 2, 3 cubes. So, we should have put probability of prime here. Probability of prime is 3/10. Probability of cube, just put that, is 3 out of 50. And that's it. 3 out of 50 is the best we can do. We can't simplify that fraction anymore. Okay, let's move on. A lot of vocab there. Card is picked randomly from a standard deck of 52 cards. Find the probability of drawing the given card. So 11. What's the probability of getting a king of diamonds? Okay, the probability of the king of diamonds. Okay, how many outcomes are in that event? Only one. There's only one king of diamonds. How many outcomes are there altogether? 52. 1 in 52. One card, you're looking for one specific card out of 52, your probability are going to be 1 out of 52. See, I almost said odds instead of probability. Happens all the time. A card other than a 2, so the probability of not a 2. Okay, that's pretty straightforward. It's a good enough description. So probability of not getting a 2. So how many cards are not 2s? There are 52 cards. 4 of them are 2s, so 48 of them are not 2s. 48 are not 2s, and 52 altogether. So we got 24 out of 26. Yeah? And then 12 out of 13. 12 out of 13 are not 2s. And this 13, this comes up a lot when we do probabilities with cards, because there's 13 cards in each suit. 12 cards in each suit are not 2s, so that definitely makes sense that would come out that way. Number 17. Yeah, number 17. Lotteries. When we talk about probability, I get on my soapbox about lotteries. Don't play the lottery. It's ridiculous. It's as a somebody I respect in financial advice says it's a tax on the poor, and it really is. You don't see a lot of people who are rich playing the lottery. People do win the lottery and they do get rich, but 100% of them gain weight. That's one statistic, and most of them go bankrupt. So uh, it just doesn't even improve your life. So don't play the lottery. You'll never win. I can say that pretty definitively. So what are we gonna do here? Looking at the rules here. Assume the numbers are picked randomly. You must correctly pick 6 out of 48 numbers. The order of the numbers is not important. Okay, let's go back to that specific definition of probability, and that is, first you need to know the event. So the event is, pick 6 out of 48 numbers correctly. Without respect to order. So if the 6 numbers that are picked are 1, 2, 3, 4, 5, 6, any order that you get of those, 6, 5, 4, 3, 2, 1, that would win too. 6, 3, 1, 2, 5, 3 would win as well. Yeah. Anyway, so it does not matter about the order. The way that the numbers are picked, when we pick them, we want to just not care about the order of them, okay? So we want to know, what is our probability of winning? The probability of winning this particular lottery. Well, we buy a ticket. We have one ticket, right? One ticket. Okay. And there's a couple different ways. Let's count this in a couple different ways. This is the way that occurs to me. When it says that order is not important, that tells me that when they pick 6 numbers, all I care about is the combination of the numbers, not the order of the numbers. Okay, so that goes back to permutations and combinations, 10.1 and 10.2. So when they pick the numbers, I'm not looking at what order they're in, I'm just looking at what combination of numbers there are. So I just care about, when I want to know my probability of winning, how many combinations of numbers are there, right? How many ways are there to pick 6 numbers out of 48 numbers and not care about the order? Well, not to care about the order means to use combinations. We're picking out of 48 numbers, and we're going to pick 6 out of them. Okay, so that's 1 in, let's see what this number is, 12,271,512. Okay. You might want to, the probability of winning this lottery is quite a bit better than your typical multi-state Powerball lottery, where the order is important, but then again you're not going to win as much. So it's just never worth your time to play the lottery. Here's another way of thinking of it, because you're thinking, well, no, because not just one ticket will win, lots of different tickets could win, right? Because I could do 1, 2, 3, 4, 5, 6, 6, 5, 3, 2, 1. There's all these different ways to win, right? So let's think of it a different way, probability of winning. Well, how many tickets? There's only 6 numbers that you can pick and win, right? 6, 5, 4, 3, 2, 1, 2, 3, 4, 5, 6. If the 6 numbers are 1 through 6, then you win however you put those numbers together, okay? And I totally understand that you may be thinking, don't just count one, count them all. Count all the tickets that you could possibly win with, right? So let's think about that. Well, there are 6 numbers. They're all different. They all got to be different. They can't be the same number. You can't have 6 in there twice. And then you think, so how many tickets would that be? How many tickets can I win with? Well, there's 6 things, and you want to arrange them in all the possible ways you can arrange them. So that's 6 factorial. That's the definition of 6 factorial, at least for us. When we count things, that's the definition. Okay, but then how are you counting the numbers? You're counting them, when you use 6 factorial, counting them with respect to order. You're saying that the order is important. you're giving importance to the order by counting all of the different orders. I'm saying don't count all the different orders. Just say there's one ticket, or there's one combination. Say one combination of numbers that wins, and then count all the combinations. If you count it this way and say all of the tickets that I could possibly make with those 6 correct numbers, all those tickets win. But then you would have to count all the possible outcomes, all the possible lottery picks with respect to order. Because by counting them this way, you are giving importance to the order. Okay, so then you'd have to count just the permutations of 48 things, picking 7 or 6 at a time. Now you want to count all the permutations, and I guarantee, do it yourself, it will simplify to this guy right here. It'll be the exact same thing. Okay, I hope that made some sense. When you count them this way and you say, let's count all the tickets that you could win with, that's 6 factorial tickets, you think, well, that's better. That improves my probability of winning, but it doesn't, because when you count this with respect to order, then you need to count this with respect to order. Right? You're counting all the possible tickets, all the possible orders, so you need to count all the possible tickets and all the possible orders in the denominator as well when you count that probability. All right. Number 36, I think that's what I want. No, I want to do number 20, actually. Jumping back to 20. So let's actually undo that. Let's talk about the experiment. The experiment is choose a marble from a bag. The bag contains 10 black, so pick marble from bag containing 10 black. What's next? 8 red and 6 blue. No, 4 white and 6 blue. 4 white, 6 blue. So BL will be black and just B will be blue. That sounds alright. So what are the odds in favor of choosing white? So odds in favor of white. Okay, so odds in favor, that means the number of outcomes that will give you a white. So how many outcomes will give you a white? There's 4 of them. There's 4 ways to get a white. Oh, we have an H there. So 4 out of how many ways will you not get a white? Okay, so this is a slightly different probability. What we would look in probability is how many outcomes are there total. In odds in favor, we're saying how many ways does it happen, how many ways does it not happen. Okay, so that would be the comparison between these two numbers. So this will be, what, 18, then another 6 would be 24. So 1 and 6. So your odds are 1 to 6. 1 to 6. Okay, now this isn't part of the problem. This is the number 20. But let's just turn it on its head and say, what are the odds against? And typically you'll hear odds against. When you hear odds reported in a boxing match or at the horse track or whatever, racetrack, you'll hear odds against. So the odds against are just going to be the reciprocal of odds in favor. So we already know it. It's 6 to 1. 6 to 1. And really you would write it like this, like a ratio. 6 to 1. And you would just expect to lose 6 times for every 1 time that you win. That's how odds work. Okay, and you can tell that we really value odds because we use 4 problems out of 6. 6 out of all the problems in the homework are dedicated to odds. So, not a lot. 7. So just a few, whatever. Making a point and disproving my own point. We're more concerned with probability. This is what I'm trying to say. So, number 30. All right, and there's a little table they give us. So this is all about experimental probability. They actually did this experiment 150 times and just recorded how many times each of these things happened. So they got a 127 out of 150 times. 22 out of 150 times they got a number 2, and so on. So for number 30, rolling a number less than 5, what is the experimental probability of rolling a number less than 5? Well, all of these numbers are less than 5. So how many times out of those 150 do we get a number that was less than 5? We just add them all together. And let's just grab our calculator real quick, because that's just going to be real simple. Clear this out. 27, 22, 18, an amazingly low number of times for number 3, and 26 times. Altogether, we get 93 out of 150. I just divide that by 150. I don't think we're going to get anything nice here. Let's say, turn that into a fraction. 31 out of 50, or 0.62. Let's just go with 0.62. Actually, it's equal to 0.62. Alright, so that's our experimental probability. How does it compare to the theoretical probability? Well, theoretically, there are 4 things that are less than 5. So we should get 4 out of how many total outcomes are there? There's 6. So 4 out of 6. 2 out of 3. Or 0.66. Approximately, because it's repeating. So 0.62 versus 0.66, pretty close. The experiment came pretty close to being the actual theoretical value. Okay. So there you go, comparison of experimental and theoretical. 36, we've got this shape here, like that. And you go like this, and see how these being labeled. Looks like they're giving us, this is the center, they're giving us this 16 here is, you can see there's a blue line right there on the book. That's a diameter of 16. Yeah. Yeah. So if you threw a dart at this figure, and shading this in so you can tell the difference, at this perfect circle, thrown into this kind of a triangle, where this, we can see that the vertex, or the top of this triangle here, is straight up from the radius, or from the center of the circle, right? So we can assume things like this is a radius of the circle, and that these two sides then must be equal to each other. Okay, these are all things we need to be able to assume. They don't take long to figure out. What's the probability that our dart, if thrown truly randomly, will land in this shaded triangle? Okay, so it's hard to count the outcomes. You know, how often will your dart land in here? Well, there's just an infinite number of places it can land. It can land here, and then right there, and right there, and there's just an infinite number of possibilities just inside that little circle there. So how do we count the number of outcomes versus the number of outcomes on the total circle? Well, let's just look at how much of the circle this is taking up, and we'll say, well, like whatever percentage this is of the entire circle, that would be the probability of us hitting within this triangle. Makes total sense. So let's find the area of this triangle. The area of a triangle is, area of a triangle is 1/2 base times height. Then we need the circle. Area of the circle is pi r squared. So we just take the area of the triangle over the area of the circle. So that's 1/2 times base, which is 16, times height, which would be 8, according to that picture, over pi times r. R is going to be from here to here, that radius. That's going to be 8 squared. Okay, so let's see, a factor of 8 cancels with that factor of 8. There's a factor of 8 in 16, so that cancels out this 8, and this goes to 2. 2 times 1/2 is 1, so 1 over pi. 1 over pi, or 0.318. Okay, so a little less than 1/3 of the time. A little more than 1/3 of the time. What am I thinking of? Little less than 1/3 of the time. 1 out of 3.14. And that will be everything. So thank you for watching.